Today, we're taking a look at two of the most impressive rocket engines of our time, SpaceX's Raptor and Blue Origin's BE-4. Two completely different philosophies, two opposing development strategies, but both with the goal of revolutionizing space travel. In one corner, we have SpaceX with the Raptor engine, which is designed to pave the way into a new era of space travel with brutal power, maximum chamber pressure, and maximum reusability. In the other corner is Blue Origin with the BE-4, which focuses on reliability, smooth throttling, and proven technology. And above all, it ensures that Jeff Bezos actually gets his rocket fleet into orbit. And then we'll tackle another extremely exciting question. Why does Blue Origin use hydrogen for the upper stage, while SpaceX relies entirely on methane? Is that smart, or is it a strategic misstep? So buckle up. It'll get technical, nerdy, and most importantly, fascinating. Chapter 1. The bare numbers. Who has the greater thrust? The question of all questions, who has more power? Here we have the ultimate comparison between the two most advanced methane engines in the space industry, Raptor 2 from SpaceX and BE-4 from Blue Origin. Two completely different philosophies, but both with a clear goal, maximum performance at minimal cost. In terms of thrust, the engines are about equal, with the BE-4 delivering a bit more power at sea level, 244 tons versus 230 tons for Raptor 2. In terms of image signal processor efficiency, the Raptor is clearly ahead. With 350 seconds in vacuum, it is more efficient than the BE-4, which reaches 330 seconds. That means the Raptor gets more energy out of the same amount of fuel. It should also be clear that Blue Origin designed the BE-4 for atmospheric use, not for vacuum operation. That's why image signal processor isn't everything. Things get interesting with chamber pressure. The Raptor operates at 330 bar, while the BE-4 is only at about 180 bar. That shows the fundamentally different strategy. SpaceX relies on maximum efficiency, maximum performance, and maximum stress for the hardware. Blue Origin takes the more relaxed approach with lower pressure, less material stress, and therefore a longer lifespan. So far, everything is still theoretical, because no BE-4 has been reused yet, and Raptor 2 has only been reused once so far, during Flight 7. Strategically, that's exactly where SpaceX and Blue Origin want to go. Reliable and sustainable reusability of all systems, especially the engines. But let's get back to our table. When it comes to the thrust-to-weight ratio, or TWR, the Raptor dominates with 107:1, while the BE-4 comes in at 80:1. This means the Raptor delivers more thrust per kilogram of weight, making it more compact and lighter. Lower weight usually leads to reduced manufacturing and maintenance costs. Both engines use methane and liquid oxygen, the perfect choice for future missions since methane can be produced on Mars. And here is probably the most striking difference. While the BE-4 has only flown 11 times so far, 267 Raptor engines have already been tested in real missions. SpaceX produces engines on an assembly line, while Blue Origin is still at the beginning of the ramp-up phase. Conclusion: Raptor is more compact, efficient, and cheaper, but also riskier. The BE-4 is more robust, possibly more reliable in the long run, but heavier and more expensive. Which concept will win? The next few years will show. So, what do we learn from this? The Raptor has lower thrust than the BE-4, but it's also lighter and more efficient. And the massive diameter of the Starship allows for the use of large quantities. This creates significant engine redundancy. We saw during the first Starship test flight how far the system can go with several engines failing. While SpaceX prioritizes maximum performance, Blue Origin opts for lower chamber pressure, taking a safer approach with less long-term engine stress. The BE-4 also lagged behind in redundancy. With the current thrust, not a single engine is allowed to fail at launch. Otherwise, the rocket will fall back to the ground. Later in the flight, things change again. Blue Origin apparently trusts their engine's reliability. Rightly so. As has been shown so far, 2 BE-4 engines were successfully used in the first 2 Vulcan flights, and then another 7 in the first New Glenn flight. That's an incredible achievement. Or to put it another way, the Raptor is the crazy hypercar dragster, while the BE-4 is the elegant luxury tour bus. Now it gets interesting. Why is the Raptor cheaper, and what does that mean economically? Before that, I want to quickly thank the supporters of the channel. You make Mars Chronican possible. We're very close to reaching the 20,000 subscriber mark, and we need your help to achieve that. Share your favorite Mars Chronican videos on your social media and group chats. Subscribe to Mars Chronican for weekly space updates, and sign up for the brand new newsletter on the website at marschronican.space. And get the latest space news, exclusive background information, and discount codes. In the shop, you'll find a new design every 4 weeks. Feel free to check it out. Every purchase directly supports Mars Chronican, and check the video description for some interesting discount codes. Support the channel on Patreon or become a channel member and enjoy the latest issues as soon as they're finished, not just when they're released. But now back to the question of cost effectiveness. Why is the Raptor cheaper, and what does that mean economically? There's a good reason why SpaceX produces the Raptor 2 for just $1,000 per kilonewton of thrust, while Blue Origin pays 3 times as much for the BE-4. The reason is simple: manufacturing, scaling, and philosophy. First, the production philosophy, quantity over quality, or both. SpaceX follows a strategy that was long considered insane in the space industry. Iterate rapidly, fail often, learn fast. Instead of spending years developing a perfect engine, SpaceX relies on rapid prototyping, radical testing, incremental improvements, and mass production. This has led to more than 250 Raptor engines already having flown, while Blue Origin can only boast 11 flights with the BE-4. Blue Origin, on the other hand, relies on a more traditional approach, more conservative development. The result? The engine is indeed mature, but heavier and more expensive. Second, material and manufacturing. SpaceX prints, Blue Origin mills. A decisive factor for the lower costs of the Raptor 2 is the radical manufacturing method. While Blue Origin relies on traditional metalworking with elaborate computer numerical control milling for the BE-4, SpaceX uses 3D printing for entire engine components. That doesn't always mean less work. Raptor consists of significantly fewer individual parts because many components are printed as a whole. That saves costs and reduces potential sources of error. SpaceX can currently produce at least 1 Raptor per day. This information is already a bit outdated. With the switch to Raptor 3 production, the output will probably increase significantly again. Blue Origin now makes about 1 BE-4 each week. That will probably get much faster in the coming months. After all, they also have to supply the Vulcan. And then there's the chamber pressure. The Raptor runs at up to 330 bar, while the BE-4 only reaches 180 bar. That means the Raptor generates more power with a smaller engine. Smaller engines mean less material is used, which saves costs. Third, economies of scale, the importance of production volumes. SpaceX mass produces the Raptors because Starship needs 33 of them per booster. This allows SpaceX to produce extremely cheaply, similar to the mass production of cars. Blue Origin, on the other hand, only needs 7 BE-4 engines for a New Glenn and 2 each for Vulcan. That means less demand, less scaling, and accordingly higher costs. Fourth, reusability. Who can fly more? Reusability changes the economics. SpaceX designs the Raptor so that it can withstand up to 1,000 flights without major maintenance. At least that's the plan. I think we'll only know for sure once the first Raptor 3 engines are in use. Blue Origin states a minimum lifespan of 25 flights for the BE-4, but no BE-4 has undergone this endurance test yet. The same applies here in the long run. Blue Origin will certainly do everything they can to get more out of their engines. The faster they can reuse their engines, the quicker the effective cost per launch will decrease. But costs aren't the only factor. Especially in the case of Blue Origin, where Jeff Bezos is known to have no problem injecting more capital as needed. Although it should also be said that SpaceX isn't really lacking potential investors either. What does all this mean for the future? The cost structure of the engines will determine which company dominates the space market. SpaceX relies on radical cost reduction through scaling and efficiency, while Blue Origin focuses on long-term stability. But one thing is certain, both engines have the potential to change space travel forever. But now comes the big question. Why did Blue Origin actually choose hydrogen for their upper stage in the first place? And was that a good decision? We'll explain that next. Why does Blue Origin use hydrogen for its upper stage? Methane or hydrogen? That's almost a philosophical question in spaceflight, with very real technical and economic consequences. While SpaceX consistently relies on methane, Blue Origin uses liquid hydrogen or liquid hydrogen 2 with liquid oxygen for New Glenn's second stage. But why? And was that a clever decision? Here are the advantages of hydrogen as rocket fuel. Hydrogen has some impressive properties on paper. Liquid hydrogen 2 is the most efficient chemical rocket fuel when it comes to specific impulse. The BE-3U engines from New Glenn achieve over 450 seconds in vacuum, while the Raptor 2 is at 350 seconds. That means with the same amount of fuel, and liquid hydrogen 2 stage can fly farther. Since hydrogen has a low density, the tanks are lighter, which enhances the mass efficiency advantage. Liquid hydrogen 2 and liquid oxygen have been used for decades in the Saturn V, the space shuttle, and the Ariane 5. That means the technology has proven itself. Blue Origin has also perfected the handling of liquid hydrogen over the past 25 years. The dark times of hydrogen and why SpaceX avoids it. Hydrogen is a nightmare for engineers in practice. Extremely low temperatures at -253 Celsius. Hydrogen is the coldest cryogenic fuel, which makes it difficult to store. It evaporates easily, has to be constantly cooled, and requires highly complex insulation systems. Extremely explosive and penetrates nearly everything. Hydrogen molecules are so tiny that they can diffuse through metal structures and cause leaks. Even tiny leaks can lead to dangerous explosions. Because hydrogen is so low in density, you need very large tanks. This makes upper stages heavier, bulkier, and increases air resistance losses during flight. Expensive and difficult to handle liquid hydrogen is expensive, complicated to store, and can put a heavy strain on infrastructure. See space shuttle fueling with hydrogen leaks as a constant problem. SpaceX avoids hydrogen for exactly these reasons and instead uses methane, or CH4, for the Raptor. Methane is much easier to store, has a higher density and therefore smaller tanks, and requires less complex cooling systems. Did Blue Origin make the right choice? That depends on how efficient the BE-3U engines actually are. In any case, from today's perspective, they will not be reused. Hydrogen could be ideal for long-term missions, but not for an economical, frequently launched, low-maintenance rocket. There's still a big question mark there. Blue Origin is sticking to the conservative approach to spaceflight with all its advantages and disadvantages. SpaceX, meanwhile, pursues aggressive efficiency and scaling. But no matter which strategy is more successful in the long run, one thing is clear. Both Raptor and BE-4 will help shape the future of spaceflight. And that brings us to our big question. What does the future of engines look like? What upgrades are planned, and what role will they play in upcoming missions? We'll clarify that in the next part. The future of Raptor and BE-4. Who has the better upgrades? If you think that the Raptor 2 and the BE-4 have already reached their final design, then you're underestimating the drive for innovation of these two competitors. Because both engines are still being developed, and the upcoming versions could be even more efficient, more powerful, and maybe even more revolutionary. The Raptor 3, even more thrust, less weight. SpaceX has already built and tested the first version of the Raptor 3. And the upgrades are significant, 50 tons more thrust than the Raptor 2. That's about 280 tons per engine in vacuum, and around 100 kilograms lighter. That further boosts the thrust-to-weight ratio. Simpler construction and faster production, SpaceX wants to ramp up the production rate and has designed Raptor 3 so that it can be manufactured even faster. Higher chamber pressure, probably over 350 bar, which means SpaceX is getting the absolute maximum out of the thrust. Eventually, the physical limits of possibility will be reached. When that happens, it will be time to turn our attention to a different kind of propulsion technology. It's still a bit too early for the topic of nuclear propulsion. I've made a separate video on this topic called To Mars in 45 Days. You can find it linked below. Right now, everyone is busy with the Raptor. Elon Musk already said that later versions of the Raptor could reach over 300 tons of thrust. That would give Super Heavy Booster 9,900 tons of thrust. And who knows? Maybe more Raptor 3 engines will fit under the booster than Raptor 2, so possibly an additional 300 to 900 tons of thrust. But why is SpaceX pushing the performance so much? It's simple. More thrust means smaller rockets for the same payload, or more payload for the same rocket, cost reduction through fewer engines per booster, and higher efficiency for interplanetary missions. The goal is to make Starship ready for use faster than ever before, for Mars, the Moon, and beyond. 2. Blue Origin. Will there be a BE4 Plus or BE5? At Blue Origin, the roadmap is less clear. Officially, there is no confirmed successor to the BE4 yet, but there are hints. A potential thrust increase from the current 2,400 kN on the ground to 2,700 to 3,000 kN is certainly conceivable, especially when you consider that Blue Origin is working with extremely generous margins here. If you get closer to the load limits of the materials, then even more might be possible. Either way, they're developing a reusable upper stage. That could mean they're planning an entirely new engine, maybe a BE5. Because sooner or later, they won't be able to avoid developing a larger, fully reusable system. There's always talk about a new Armstrong, but that's not official. The way I see Blue Origin, I'm sure they already have a few more irons in the fire, but what about profitability? Which engine is more cost-effective long-term, and why? We'll cover that next. The profitability of Raptor and BE4. Who has the better business model? Technology is one thing, but how economical are the two engines? After all, it's not just about thrust and efficiency, but also about how expensive an engine is, how many times it can be reused, and what the production rate is. And this is exactly where the real competition between SpaceX and Blue Origin begins. First, the production costs. How much does an engine cost? Raptor 2 costs about $250,000 to $300,000 per engine, while the BE4 is around $10 to $20 million per engine. Yes, you heard that right. A BE4 costs about 40 to 60 times more than a Raptor 2. This leads to a huge cost gap between the two engines. A super heavy booster with 33 Raptors costs about $10 million, while one with 33 BE4s would cost over $300 million. It should also be clearly stated that the internal costs may actually be lower than the stated 10 to 20 million. Blue Origin also makes extra business from selling the BE4 to the Vulcan. Second, production rate. Who can build more engines? SpaceX is currently building at least 365 engines per year and aims to raise that number to 1,000. Blue Origin is currently producing 52 BE4 engines per year at its current pace, but that will get much faster. So I wouldn't be surprised if Blue Origin quadruples that number in the next 24 months. That means SpaceX wants to produce enough Raptors for 2 to 3 super heavy boosters per month. Blue Origin might only be able to build a New Glenn first stage every 2 months. SpaceX currently leads with Raptor 2 and soon Raptor 3. Long term, it's unclear if Blue Origin can respond with a better BE4 or reusable upper stage. But one thing is clear, the engine race is far from over. What do you think? Which technologies will prevail in the long run? Will Blue Origin succeed with hydrogen, or will methane remain the undisputed standard? Let me know in the comments. My name is Serwan, and this was Mars Chronican. Thanks for watching. And as always, per asper ad astra.